This is a video for statistics, day 1, review of statistics from Algebra 1. So when you took Algebra 1, you spent some time doing some work with statistics. So this lesson is about reviewing a lot of concepts that should be familiar to you from Algebra 1, and then we will continue to build upon that as we go throughout the rest of the unit. We'll be doing some work with the calculator a little bit later, so you should grab your calculator and have it handy for when we get to that part. So we're going to start by looking at some histograms, some bar graphs. And it says distributions are described by the shape as being symmetric or skewed, the center, and the spread, which is the variability of the distribution. And we'll talk about what all of those concepts mean. So it says a distribution that is approximately symmetric can take different forms. So we have some examples of some symmetric distributions here. It says a distribution is described as mound-shaped. Sometimes they'll also use the word bell-shaped. If it is approximately symmetric and has a single peak, like in the example on the left. So this is one that we would say is mound-shaped or bell-shaped. You can imagine, if you sort of connect the bars there, yeah, it's pretty good. You get this nice bell-shaped pattern to it. This one's symmetric, but it doesn't have that bell shape going on. And then it says a distribution is skewed to the right or skewed to the left if one of the tails is longer than the other. We have an example of one of each one of those. So yeah, if you imagine kind of connecting the bars like I did earlier, you know, this one's got a much longer tail on the right-hand side. And so the tail is longer on the right when it's skewed to the right. And then this one is skewed to the left. Then we've got a much longer tail coming on the left side than we do on the right side. So bell-shaped, symmetric, right? Or symmetric and not bell-shaped, and then skewed to the right, skewed to the left. The mean of a distribution is interpreted as a typical value and is the average of the data values that make up the distribution. So the mean is the average. It is often represented by this symbol here, which we read as X bar. Okay, so X with the bar on top, X bar, that represents the mean. And then we're also going to be talking about the standard deviation. Standard deviation is a value that describes a typical distance from the mean. It is often represented by this symbol, which is Greek letter sigma. Okay, so sigma for standard deviation. Just regular symbol represents the standard deviation for the entire population, which is what we'll be looking at. On to the next page. Okay, so we have some more histograms. We're going to be looking to match up the properties of the histograms. Okay, so consider the following histograms 1 through 4. We have some descriptions down here at the bottom. And we're going to match up which description goes with which histogram. So match the description of a distribution with the appropriate histogram. So just sort of looking at them all together here, I can see that these two on the left kind of follow that bell pattern, right, where these two are skewed, both to the right actually. So I'm going to say these ones are bell-shaped, right, or mound-shaped, as it says down here. And then these two are skewed to the right. Okay, so starting to match up which one goes with which graph. You'll notice that the means of all of them are identified as being the same. So if you look at our histogram, right, so they're computing the means to be 100 for all of them, so that doesn't really help us break it down. But we do have some difference in the standard deviation. So the standard deviation is a measure of how far a typical data value is from the mean. So that means if your standard deviation is larger, your data values are going to be more spread out. They're going to have a wider range. So I'm going to say bigger sigma, right, implies that your data is more spread out. Okay, So if I start with, B and C, which are my bell-shaped ones, my mound-shaped ones, let me look at the range of my data values here. So this one goes from 70 to looks like about 125. Right, and then this one goes from 0 to 200. Okay, so if you say which one is more spread out, that would be the one that goes from 0 to 200. Right, so this one should have the larger standard deviation. This one's going to have a smaller standard deviation. Okay, so histogram 1 should be the mound shape with the smaller deviation, right, which would be B. And then histogram 3 is going to be the mound shape with the larger standard deviation. Okay, so 3 goes with C. Okay, and then we have our two graphs that are skewed to the right. And to help us figure out which one's which, we can look at the range of values. Okay, and again, I'm estimating here. Let's see, it's a little hard to tell. Is that like 80, 85-ish, right? Up to like 150, let's say. Oh, they're going up by 5s. Okay, I can see that. Okay, so how about 85 to 145? Okay, and this one here is going from about 50, oh boy, about 325-ish. Okay, so this one definitely more spread out. So this last one here, histogram 4, should have the larger standard deviation. Okay, so histogram 4 is going to be the one with the standard deviation of 40, right, which leaves 2 to be A, skewed to the right, and the smaller standard deviation. Okay, so standard deviation measures how spread out your data is, and then looking at the shape of the graphs. Okay, we have one more histogram to sort of analyze and answer some questions. So the histogram below shows the distribution of the greatest drop in feet for 55 major roller coasters in the U.S. Okay, so we've got feet, the feet of the maximum drop here, and then we have the frequencies of the number of roller coasters that have that. That's what they're measuring. Okay, so it says, would you describe this distribution of roller coaster maximum drops as approximately symmetric or as skewed? So I would look at this and say, definitely looks like it's getting skewed to the right, right? There's some extreme data values out here. So if I connected, again, the bars, I would need to have a longer tail on that right-hand side. Okay, so skewed to the right, and then I'll say there are some extreme right data values affecting the curve. Okay, so skewed to the right, there are some extreme right data values affecting the curve. Letter B asks about the mean. Is the mean of the maximum drop distribution closer to 90, 135, or 240? And explain your answer. So we can find the mean by sort of trying to find where the center of the bell is, close to the center of the bell. So sort of looks like it would be like right about here-ish, right, for the mean. Label that as X bar. So I would say X bar closest to 135. Right, 90 way too far over, 240 way too far over, right? So closest to 135. Again, the mean's always going to be closest to the center of the bell, right? Which is where your data values are concentrated, right? We're sort of ignoring those extreme values. So closest to the center of the bell without the extreme data values. That's where we can find the mean. Okay, and then it says, is the standard deviation of the maximum drop distribution closer to 40, 70, or 100 hours? Explain your answer. Well, this one's a little trickier to figure out. If we try to measure out kind of what's happening here. So if I go out 40 from the mean, right, so 135 plus 40-ish, and then 135 minus 40-ish, right? So that's plus 40 minus 40. That. If I go out 70 from my 135, right, so 70 from 135 is going to put me kind of about here. 70 out that way is going to be about here. I just realized I labeled these backwards. Okay. Okay, that was supposed to be plus 40. This is supposed to be minus 40. Okay, now I've got minus 70 plus 70. Ooh, hard to write small on here. Sorry, guys. Okay, and then if I go out 100, right, that would put me like up to here, and 100, that would put me like down to there. Minus 100 plus 100. Okay, so if I'm trying to figure out which of those makes sense to be the standard deviation. So standard deviation means that most of your data values are like that far away from the mean. So, you know, if I look at 40, I would say I'm not sure if that's the best one because there's still a lot of data values that are not in that range. 70 seems to include most of the data values. But then, you know, if you go out to 100, this is almost like going too far, right? There's like some extra space over here. So out of the three, I think 70 is the best, right? So I'm going to say sigma is approximately 70, right? Standard deviation. Again, this one's not quite as obvious, but hopefully this sort of makes sense. So it's a typical distance from the mean. You know, so it's not 40 because I would say most data is farther away than plus or minus 40, right? And then it's not 100 because that includes too much data is within your plus or minus 100. And so out of the three options, 70 is going to be the best bet for the standard deviation. But we're going to learn how to calculate that as you'll see, so it'll be easier to figure out. Okay, we're moving on to our calculator portion. So grab your calculator so you can do this along with me. So following are the number of calories in a basic hamburger, 1 meat patty with no cheese, at various fast food restaurants around the country. So we've got quite a few data values here. There are 32 values altogether, and that will help you when you're punching them into the calculator. Because as we've seen before, when we have data we want to analyze, we're going to put it into our list. We're used to doing this when we calculate regressions. The inputting of the data is the same, but we're going to be doing a little bit something different with it today. It says input these data into L1 on your graphing calculator, and then we're going to use 1var stats to calculate the mean and the standard deviation. Okay, and I'll show you what all of that looks like. So I'm going to pull up my calculator here. To enter things into the list, right, we go to stat and then to edit. Now I actually have all of these typed in because it took a few minutes on this graphing calculator app. But feel free to pause this video and you can get the data in and then start it up again when you're ready to go. Okay, so once your data is in there and you're ready to find your mean and your standard deviation, we're going to go over to stat and calc like we do with our regressions. But when you want to find the mean and the standard deviation, we're going to be calculating what's called the 1var stats. It's the very first thing there. So you're going to hit enter on the 1var stats. Okay, now if you have a newer calculator, right, it's going to look like this. So, you know, your list should say, whoops, it went away. Your list should say L1, right, and then your frequency list right now, right, should be blank. Okay, if there's anything in there, you can arrow it and hit delete, right, and clear it out. If you have an older calculator, okay, if you hit an older calculator, when you hit the 1var stats button, it just takes you to the home screen and it just says 1var stats blank. So you have to put in this case, we're just talking about L1. Okay, so when you do second and 1, right, that gets you to the L1. So you would want your screen you know, to look like this here. Okay? And then you hit enter and it will calculate it for you. Okay, newer calculators. Oops, let me go back to this. Okay, newer calculators are going to hit enter. All right, enter and then hit calculate. So when you hit calculate, and either on the newer or the older calculators, all of these fun statistics come up. Okay, so what we are interested in right now is the mean, which is the x bar. Okay, so I'm going to write down x bar, and then doesn't say what to round to. Okay, but we can just take them all. Okay, 665.3125. There's a way to get that up at the same time. Okay. Then I want to find the standard deviation. Standard deviation is the little sigma. So there it is right there. All right, 278.963. Okay, so sigma x is equal to 278.963. Okay, and standard deviation, represent that with the little sigma. And then the mean is the x bar. Okay, we can have our calculator actually show us a histogram for all of this, which is a cool thing to do. We have to set it to be the histogram though, because right now it's probably on scatter plot. So we're going to go into our stat plots. So this is go to second and y equals, that's into your stat plot. You can turn your stat plots on this way. And then we're going to select down here, first of all, you're going to turn them on. And then in this type section, you want to arrow over till you see the little histogram one, right? And highlight that. Okay, should say L1 in your X list 1, right? Should say frequency of 1. And if you have an older calculator, you may have some different stuff in there. But as long as you select the histogram, it should be fine. So you won't have the color option if you have an older calculator. But then once that's on there, right, and you hit zoom 9, there it will put together a lovely histogram for you. Let's see if I can shrink this and make it go side by side. Please hold. Okay, there we go. All right, so we could sketch out our histogram. All right, so we got a bar like this. I have a lot of bars that are the same height there. 3 more, a little shorter one like that. Okay. So what sorts of things could I say to describe my histogram? You know, I would say that's roughly symmetric. Right? Roughly symmetric. You could argue that it's skewed to the right. We've got some values over here. Either one's probably fine. Okay, friendly reminder, if you go over to y equals, you'll notice that your plots are on right now because we graphed something with statistics. So when your plots are on, you cannot graph other things. So you can turn your plots on and off right from here. Just arrow up and hit enter, right? So now they're off. But you're still in that histogram mode, so if you want to do a scatter plot, you have to go back and change that. Okay, on to the next page. We got one more calculator question here. So sometimes we get a single list of data, like we saw in that previous example, but then sometimes you get a frequency table. Right, so a frequency table gives you the number of times that data value occurred. Right, so we had to slightly alter what we do in our calculators to figure out the mean and the standard deviation. So it says the table below displays the number of siblings of each of the 20 students in the class. So I have the number of siblings, and then this represents the number of students in the class that actually had that number of siblings. So if I wanted to list out all my data points, right, there'd be like 2 kids that had 0 siblings, and then 3, 4, 5 students that had 1 sibling, and so on and so forth. Right, so instead of listing out all the data values, they organize them into this nice little table for us. Okay, so the good news is your calculator can figure out the mean and the standard deviation and a whole bunch of other stuff, as we'll see momentarily. But this time, we're going to have to make use of both L1 and L2. Okay, so enter the number of siblings into L1 and the corresponding frequencies into L2. Determine the mean and the standard deviation. Okay. So, let me pull up the calculator again. So I'm going to go back to Stat, Edit. Okay, I'm going to clear out my hamburger numbers, maybe, if I can figure out how to do that. I can't tell if it's thinking or what. What are you doing? Please hold again. Did it freeze? It looks like it froze. Okay. Let me see if I can pause my video.